This conference will now be recorded.
And let's take a look. Okay, so question number 4 on packet number 1 is one of these kind of qualitative problems in gravitation. So the way to kind of get started on something like this is we want to figure out what the person's weight is. Well, we know that weight is the downwards force, and it's a function of how big the planet is and how massive it is underneath it. So we can write Newton's universal law. Oh, I didn't share that screen. Give me 1 second and I'll back up. My mistake. All right, so you guys should be able to see that now. I had started to write and talk about, okay. Awesome, make sure that that problem got fixed for you. All right, so let's go back and take a look at question number 4. We have a weight directed downward. We'll call that the force of gravity. And we know that there's some sort of a planet underneath that. And we're going to use the universal law of gravitation. The force of gravity is equal to G times the mass of the two things. In this case, could be the mass of the planet times the mass of the thing. In this case, it's a person over the separating distance squared. In this case, the separating distance is the radius of the planet. If you're standing on the surface, the distance between the centers of mass between the person and the planet is the planet's radius. So what I'd like to do is just kind of focus your attention on just this stuff here in that I've highlighted. And what we're going to do is I'm just going to draw some brackets around that so that we just focus on those variables. And if we were on Earth, I'll make everything 1. So we'll say then that the mass of the planet or Earth is 1, the mass of the thing is 1, and the separating distance is 1. We have to remember to square it. So the value of everything in the brackets is equal to 1. Now we're going to do it a second time, except we have to make some changes. They tell us in question number 4 that the planet is twice as massive. So that variable, the mass of the planet, changes from 1 to 2. It's twice as massive as Earth. But then we're also told that the radius changes, and twice the radius. The thing that we brought there, whatever that person was, their mass doesn't change. And so now I'm going to divide that by the radius, but the radius is 2 and it's squared. So we get this fraction of 2 over 4, or 1/2. So now we can say that the force of gravity is 1/2 what it used to be. Well, on Earth, we're told that the person's force of gravity is 800 newtons. And so after we make both of those changes, we can see that it will be 1/2 of the 800 newtons. It's now 400 newtons, or answer number A. Izzy, make sure that I've answered your question on that. And I will start taking a look at some of the other things that got asked about. Weird, I don't have like a scroll bar on my chat thing here. Oh, there it is. Okay. So Corinne is asking about review packet number 2. There's some questions on there she'd like to see. So I'll bring that one up. This is review packet number 2. And the first one that Corinne had a question on, I believe, was number 5. Yeah, 5 and 6, and then 10 and 18. So let's take a look. Question number 5. I started in one of the classes. Corinne, I don't think yours, the 4A section, got to that. But it's worth looking at this one again. This is a binary star system. So we have masses, 2 stars separated by mass d. And if we were to draw in a gravitational force on this, we know that gravity is mutual. So we have an inward gravitational force on the star on the left due to the star on the right, and vice versa. So both of those forces of gravity are the same. And if we only look at just one of the stars, we can say that the force of gravity is the centripetal force. So the force of gravity is going to be G times the mass of one of the stars times the mass of the other star divided by the separating distance. In this case, it's the variable d, or the diameter of the circle, and we have to remember to square it. On the right-hand side, the centripetal force acting on that star is just mv squared over r. But r is not a permissible variable. You can see that which of the following is the correct relationship among these quantities, and none of the answers have an r in it, and we're specifically told to use d. So I'm going to then put in the denominator, instead of mv squared over r, I'm going to say that it's mv squared over d over 2. So this whole expression can be written, one of the masses cancels out. We can kind of see that there. That's the mass of the star on the left, although they're both the same, so you kind of can't tell. And then on the left, I just get g times m over d squared. And on the right-hand side, I get v squared over d over 2. That 2 in the denominator here of the denominator, this is a complex fraction, actually ends up in the numerator. I end up multiplying by the reciprocal, or 2 over d. So that gives me v squared times 2 over d. We can see then that one of the d's on the left cancels out with the d on the right, and I have to solve this for v squared. And so how did I know to solve it for v squared? Well, all of the kind of solutions are expressions for v squared. Yeah, it is weird that all of these are solving for v squared, but I kind of follow that pattern. And so now I'm going to, in order to isolate v squared, I'm going to divide both sides by 2, and I end up getting v squared on the right-hand side is equal to g times m over 2d. And that's where choice B comes into play and is the correct answer. Make sure that I've answered your question on that. Can you guys in the chat box, I've gotten a message saying that I can't, people can't hear me, but I think some people can hear me. Can you guys give me a little feedback on audio quality? Is there an issue with the mic, or does perhaps somebody's volume need to go up? Just let me know if you can hear me okay. Is it garbled in any way? Maybe it's just an internet connection on that student's end. All right, so I'm just going to keep going. So I've gotten, we've done number 5. Question number 6 was also asked by Corinne, and Ryan is asking about question number 7. So let's just kind of keep going through these and see how we do. Question number 7 is another example of one of these qualitative gravitation problems. And so we've given this hypothetical planet. It's 7 times the mass of the Earth and twice the radius. And they want to know the gravitational acceleration on the surface. Well, we know gravity on Earth, that's equal to about 10 meters per second per second. That's going to be easy. If I had something, in this case, they're not asking about gravitational force. They're asking about gravitational acceleration. It's only going to be modestly different than some of the other ones that we've done. So if I had an object falling near the surface of a planet, I would say that Fg is equal to F net. And Fg is equal to g times the mass of the planet times the mass of the thing over the separating distance squared. And F net, that's a weird F that I drew there. F net is just the mass of the thing times acceleration. So the mass of the thing clearly drops out here. So, that goes away. And I'm now left with an expression for acceleration, which is what I'm looking for. So I can see that acceleration is equal to g times the mass of the planet over r squared. Or, if I wanted to be a little more technical with the way that I write this, I can say that the mass of the planet over r squared is proportional to a. By the way, I can use the variable g. Excuse me, I got something in my eye. I can use the variable g to just talk about more generally gravitational acceleration. But in this case, I'm just going to stick with A and say, all right, well, I've got this downward acceleration, and it's proportional to the mass of the planet and inversely proportional to the square of the radius. So like we did in the previous question, I'm going to kind of like focus on doing this 2 times. The first time that I do it, I'm going to do it for Earth. So I'm going to say, all right, well, mass of the planet over the radius. Well, let's do this once for Earth, where we have a mass of 1 and a radius of 1, which gives me a variable of 1. Then I'm going to do it a second time for this hypothetical planet. And the hypothetical planet has 7 times the mass and twice the radius. I have to remember to square that denominator. So I have 7 over 2 squared, which gives me 7 over 4. So 7 over 4 is a bigger number than 1. You know, that's 3.5 times bigger. So now I'm going to look at these answers and I'm going to, no, wait a second. Oh, no, it's not 3.5 times bigger. What was I thinking? I thought that was a 2 in the denominator. I think I was looking over here. It's 7 over 4. So it's 1 3/4 or 1.75 times the size. And so now you can see that answer C is the correct answer because it is 1.7 times Earth's gravitation. Earth's gravitation is being 10. And so 1.75 times 10 is 17.5 meters per second per second. That's the gravitational acceleration on this hypothetical planet. So make sure that I've answered your question. I think that's still Corinne's question. Now we're moving on to question number 7 that I think, no, Ryan asked about 7. Okay. And it looks like I skipped 6. So I'm going to go back and do 6 and then we'll be square. Question number 6 says, a hypothetical planet orbits a star with one half the mass of our sun. The orbital radius is the same as the Earth's. Approximately how many Earth's years does it take the planet to complete one orbit? So this is an interesting question because it's talking about time. How many Earth years? So that right there should cue you that this is going to have something to do with orbital period. And orbital period has to do with orbital speed. Orbital speed is, you know, very generally, we can say that it's distance over time. Specifically to circular motion, we can say that it's the circumference of the circle over the period of oscillation, where the circumference of the circle is equal to 2 pi r over period. So now, you know, we can kind of look at this problem and say, all right, well, in question number 6, we have this hypothetical planet that's orbiting a sun. Here's the sun, and here's the planet. And we know that that there's only a force of gravity between the planet and the sun that's causing that center-seeking force, or that centripetal force. And so we kind of have to figure out how V is going to work itself into this problem. We know that the force of gravity is the centripetal force, and the force of gravity is equal to G times the mass of the sun times the mass of the planet over the separating distance squared. And the centripetal force is just mv squared over r, or the mass of the planet times v squared over the radius. Now I'm going to make some substitutions. Hopefully this stuff is starting to be a little routine. We can see that the mass of the planet goes away. It doesn't affect its orbital speed or orbital velocity. One of the r values on the left cancels out with the r value on the right in the denominator. And I'm left with v squared is equal to G times the mass of the sun over the radius r. Now I know that I've got to figure out a way to get this in, and there's my in. So all of this is equal to v squared, and now I'm going to bring in 2 pi r over period. So let's continue, and I'll just kind of switch colors. Now I'm going to get G times the mass of the sun over r, I've just rewritten the stuff on the left, is equal to v squared, which is 4 pi squared r squared over period squared. I should make this the same capital R. So now I can solve this for period. I'm going to move period squared over to the left. I get period squared is equal to 4 pi squared r squared divided by G divided by mass of the sun. And this r over here gets multiplied. So that's actually an r cubed on the right-hand side. So it's a bit of an obnoxious, um, expression, but then I can take the square root of both sides and I get 2 pi the square root of r cubed over the square root of g times the mass of the sun. So they're saying, now that I have this expression, this is kind of like where I need it to be. Now that I have that, I'm going to do the same thing that I've been doing on all these other problems. I'm going to say, all right, well, what's changed in 6? The mass of the hypothetical planet orbits a star with a mass 1/2 the mass of our sun, and the orbital radius is the same on Earth. So the only thing that changed is the mass of the sun. The radius is the same. So I could kind of go through this orbital period expression, or capital T. I could go through it and say, all right, well, period is proportional to 1 over root mass of the sun, because everything else isn't changing. 2 is just a constant, pi is a constant, the orbital radius r is a constant. That's not changing between the, case A and case B, if you will. And g is just a number. It's a very small number, but it's not changing. It's a universal constant that's valid everywhere. So I can just reduce this and say period is proportional to 1 over the mass of the sun. And since the mass of the sun, the star, the hypothetical planet orbits a mass of 1/2 of the sun. This is going to be, for Earth, it's going to be 1 over root 1, which is just 1 over 1 or 1. Now we're going to get T is proportional to 1 over root 1/2. And so root 1/2 can be written as root 1 over root 2. And then this just becomes a complex fraction, and I multiply by the reciprocal. Root 1 is just 1. And so this becomes then root 2 times the period. And now we can see where that comes from. Is this a tough question? I think it is. I think it's time consuming to complete it. I don't think that it's unfair. I just think it's tough. And I think that the key to unlocking this problem is recognizing that they were asking you a time question, and that the only choice you have to introduce time or period into the discussion or the analysis is through that expression for speed. So make sure, Corinne, that I've answered your question, that you're satisfied with that answer. Um, 10 and 18 were also asked about. And so we can kind of take a look at those and see what they look like. Yeah, okay. So question number 10 is asking about the idea of weight. It's, the refers to the force a scale registers. Question number 10 is a bit interesting. So imagine for a second, here we are on a flat surface, and there's a person standing on a scale. And we could draw a free body diagram here and say that the weight, mg, or let's call that F sub g, is equal to the normal force going up. And the normal force is what the spring scale, or whatever mechanism the scale uses, is actually reporting. So the Earth pulls down with, let's call that, 100 newtons. And there's a spring underneath the scale that is pushing back up with 100 newtons. And that's what the scale reads. So the first part of this problem recognizes, or I should say requires you to recognize that the scale is actually reading or reporting this kind of spring force. You could call it a spring force, or you could call it a normal force, however you want to. So as soon as we introduce the idea that it's curving now, if we're moving in a circular path by virtue of standing on the Earth, right? So all of us right now are moving in a circle. Our orbital speed, by the way, at our latitude is in the hundreds of miles per hour. So right now, even though you think you're stationary at your house, you have a tangential velocity in the hundreds of miles per hour. And so what that means then is that since you are actually moving in a circle, that the gravitational force is actually a little bit larger than the force, the upwards force registered by the scale. It has to be. And the reason is when we add these two things together, the downward weight force, let's call it 100, and the upward spring scale force, let's now call it 98, we have to have something left over directed radially inward, in this case 2 newtons, to provide a center-seeking force, to pull us into a circle. Now, the circle that we're going through is this massive orbit around, well, it's not an orbit, it's a motion around the Earth. So let's, at a high latitude, the circle that you're completing is larger than it is than when you get to the equator. So look how much larger the kind of circle is at the equator than it is perhaps where we live at the 45th parallel. That means that you're actually moving faster at the equator. You have a higher tangential speed at the equator than you do at the 45th parallel because you have a larger circle to go around. That means you require a larger center-seeking force at the equator than you do at the 45th parallel, which means then that the spring might actually read a little bit less. It might be 96 newtons. I'm just totally making up these numbers to try to kind of explain this concept, which would mean then that you have a larger, it goes from a 2 Newton delta to a 4 Newton delta. You have a center-seeking force of 4 newtons. So, the short answer to the question is, the closer you are to the equator, the less the spring scale reads because you require this larger normal force. So if I suppose if you're on a diet, you could get on a plane, fly to the equatorial regions and remeasure yourself. It's plausible that you have a slightly smaller measured weight at the equator than you do up here at the 45th parallel. So, that's one way to explain away why people might look better or look good after their diets on the equator. But it's such a small difference really that it's not substantial. So the idea here is that if we're talking about the weight being the force of scale registers, the effect, this kind of net effect of a difference in the scale reading is largest at the equator. So if the Earth stops rotating, we would see this letter A. I can't imagine a question like this being asked on the new format, but nonetheless, here it is. This is an old question off the old AP Physics B, and they loved these kind of obscure questions. They still ask obscure things, but not like this. This is kind of an obscure concept. And the new format is to ask about more down the middle concepts, but in obscure ways. I think you'll see more examples of the new oddities in the AP Physics 1 format when we really buckle down and start practicing for the test in the springtime. So hopefully that gives you an answer to question number A. To question number 10. I'd like to maybe take a look at one of the FRQs before we run out of too much time. So I still haven't gotten a ton of questions, but Corinne has asked most of the questions here. So we might as well just keep going and take a look at what's going on in packet number 2. Where'd it go? Oh, FRQ 2. So let's navigate to there. This is kind of an interesting question. If you haven't had a chance to look at it, the idea here is that this mass, this puck, is being pulled radially inward by a tension in the string, and the tension is being provided by the weight of these hangers right here. So, you know, if you hang a bunch of these washers on the end of the string, you're assuming that there's no friction here where it kind of goes around that turn, and so they kind of tell you that there's a little tube here. And so the circular motion defined by that dashed line is generated by the center seeking force of tension. If you spin this thing fast enough, the weight won't drop because the weight is just providing this center seeking force. One way to think about this interface is it's just acting like a pulley wheel here, just redirecting the tension from side to side to up and down. So in this equation, capital letter P stands for period. You can kind of see you know, the work here for relating period to the mass, the hanging mass. Is a, you know, tough, challenging question. I don't think undoable at all. I think you just have to buckle down and take a look at it. But Corinne's questions were specifically on parts B and C. So let's take a look at what's going on there. So we repeat the procedure with 4 different values of M2, which is the kind of hanging mass. And M1 now has these values. You know, M1 is 0.012 or 12 grams and a radius of 80 centimeters. And the data is presented below, which can be used to compute an experimental value for G. So I want to draw your attention up here to this relationship between period. It's kind of obnoxious that they use the letter P. You know, we've already established the fact that period is typically represented with capital letter T, but it doesn't matter. And so this is a question about a technique called linearization. And linearization is when you take a data set, and if you were to graph the mass of object 2, the kind of hanging mass versus the period, from this relationship up here that I've boxed in blue, we can see that the relationship is an inverse one. I could say that period P is proportional to 1 over root M2. So I basically ignored M1, R, and G and the constant 2 pi, and I'm just focusing on M2. And so if those other things aren't changing, M1, P, M1, R, G, and 2 pi, if they're not changing and I'm only changing M2, that's going to change the period. So now I have all this data, and the question is, how do I get it so that when I graph, you know, period, and I think that they say eventually where to graph it, period versus mass. If I graph period versus mass, right, if I have a mass of, let's say, 4, then it's going to be 1 over the square root of 4, or 0.25. The square root of 4 is 2, so it's going to be 1/2. So this would be 1/2 at that point right there. And if I graph perhaps, let's say, 9, which is going to be way down here for mass 2, then it's going to be 1 over root 9, or 1/3. So it's going to be like a smaller number here. So I think you can kind of see what's going on. And if I were to graph 16, which was going to be way down here, right? It's not to scale. So we're going to get something that looks like this. It's not linear. Is it quadratic? Is, you know, what's the relationship? Well, in order to check what the relationship is, you can make an attempt to kind of linearize the data, make it a straight line. And the way that we do that is by looking at this expression here, right here, that I've boxed in a second time. Let me use a different color. Let's use this cool pink color. So if we focus on just this, there's a couple of different ways for us to kind of get this to be a straight line. And we can see that the choice is to plot 1 over M2. And if I plot 1 over M2, that creates something that is directly proportional, 1 over m2. Additionally, I can square the period. So let's kind of check out what we have here. I've got in this expression up here, let me rewrite it. I have period squared. I'm drawing your attention to one of the steps that I took right before I end. I get period squared is equal to a bunch of stuff. So let me make it a proportional sign, say 1 over m2. So there's the m2 in the denominator, and there's the period squared. So if I were to graph period squared versus m2, the constant of proportionality, or the slope, would be all of that stuff. So that would actually allow me to solve for g, because I know m1, I know the radius. This is just a number, 4 pi squared, and I'd be left with just this to evaluate. That's the only thing that I'm making an assumption on. That's what they're asking me for. So I'd have to get the slope. So yeah, I think that's a tough question. But this idea of linearization pops up rarely, but it's not zero. And so you can see that when we've plotted p squared and 1 over m2, we get this linear function, and now we can take the slope of that line in order to evaluate g. It's a little messy, but not undoable. Okay, I'm going to do, I think this is a good place to sign off. I don't think that there have been any additional questions after that first grouping. I didn't get to every single question that Corinne asked, but I got through some others and a huge chunk of those. So I think I'm going to stop there. For now, no, Corinne, there will not be a linearization problem on the test. Riley is asking about a practice problem, which I think is a really smart thing to do before we sign off. So I'm just going to bring up like a blank piece of paper. We'll do a quick practice problem, maybe 5 minutes or so, and then call it done. Let me bring up a whiteboard. Actually, I don't even think I need to do that. I could just bring up Microsoft Word and use those markup tools I've been using all along. Give me 1 second to just bring up a piece of white paper. All right, I'm just going to do this. Let's go to, this is like a like an online whiteboard that I use for sharing a screen sometimes, but we'll just use it for now. And I need to change my screen sharing. Give me 1 sec. I have to minimize that. All right, so you should be seeing the whiteboard right now. If you aren't, let me know. So here is the whiteboard, and let's do a practice problem. And the practice problem will look like this. So we're going to have a car, and the car is going to be going to the right at a constant speed. And the car goes up a hill, and the hill has a radius of curvature. So this is part of a circle right here. And we'll say that the radius of curvature r is a known value. Let's make r equal to 25 meters. And the question that I have is, when the car gets to the top here, it's going around a turn, it's going around a curve, a vertical circle like that. the question I have is, what is the maximum velocity, V max, that this car can negotiate the turn without the tires coming off the road? So we want to know what that linear velocity is, or that tangential velocity is at the top of its path. We know the radius of curvature is equal to 25 meters. We'll throw the mass in there. You probably won't need it, but I'll throw it in there, and we'll say that it's 1,200 kilograms. So if you're not sure what to do or how to start this problem, it's always a good idea to start with a free body diagram. So I'm going to have you guys take a minute, and either in your notebook or somewhere else, to sketch a free body diagram of the forces acting on the car at the top of the hill. Let's call that position P, at the top of the hill. I'll give you guys a minute to do that. Well, more like 10 seconds. Okay, so the thinking is that there's for sure a downwards force, mg. And since we have the mass of the car right here is 1,200 kilograms, now technically, if we use 10 for g, that's going to be 12,000 newtons, or 12 kilonewtons. So we know what the downwards weight force is. There is, if the car was stopped at the top, there'd be a normal force. And if the car was going around the turn very slowly, the normal force would be directed upwards. And the normal force would have to be, oops, I keep doing that. Give me a sec here. The normal force would have to be less than the weight force. It'd have to be less than 12,000 newtons. And the reason is, when we add those two things together, because they're opposite each other, we can see the normal force is radially outward. Then if it has to be less, so we have something left over. Let's remember that downward is radially inward, so we'll call that positive. So our dynamics equation is going to be the weight force mg minus the normal force Fn is going to be equal to our centripetal force. So this is just kind of a general situation, like a general description or general dynamics kind of expression for this part, this kind of circular motion. Now, here's the thing. As I go around the turn faster, the normal force gets smaller, and you guys need to know that. So this normal force here gets smaller and smaller and smaller. And the smallest that it can be is when it's zero. So the normal force can get as small as zero, obviously no smaller than that. And so when the normal force goes to zero, I can say that mg is the only center-seeking force. And we know that the center-seeking force is mv squared over r, where this would then be v max. We can't go any faster around and stay on the road. We can go faster, but if we go faster, we'll be going around a bigger circle, which means then that we're going to leave the road here on this side of the hill. So, now I'm good to go on a problem like this, and I can solve for V max. The masses cancel out, and I'm left with root GR is equal to V max. And so if we use 10 for G, and we know that the radius of curvature is 25, we're going to get root 250. Well, I know that root, I got a calculator right here, so we'll see what that is and actually get a number for this. All right, so I'm getting about 15.8. And so now we can see that we have a maximum speed. And if I'm dealing with sig figs, I'd probably round that up to 16 because I have 2 here and 2 here. So I'd say 16 meters per second is probably the kind of the best answer. Anything more than that, and I leave. Anything less than that, and I stay on the hill, but then I start to produce a normal force here. The format of the test is going to be pretty consistent with what you guys have seen, just less. There probably will not be a bubble sheet. Well, there won't be a bubble sheet. It'll be like 12 multiple choice questions and maybe 2 FRQs. So that seems like the right amount to be done in 40 minutes, maybe 45 or 50. But I'll see what the final format looks like. But if we do like a minute and a half per question, it ends up being a little bit more than that, maybe like 1.7, minutes per question. 1.7 times 12 gives us about 20 minutes for the multiple choice, and then 10 minutes each for 2 FRQs. About 45 minutes, I'd say, would be ample time. So that's the plan for the test tomorrow, and I'll plan on seeing you guys in the morning if you have any additional questions for me. That's it for tonight. Thanks, guys.